In the last lecture, we had met maps between groups. We were interested in particular in maps which preserved group structure, that is to say, which worked well with multiplication. In other words, you could multiply first in the first group and then use the map to go to the second group, or you could map the elements first to the second group and then use the second group's multiplication rule to calculate the product there. And whichever way you did it, you would get the same result. Such maps were called homomorphisms. And if two groups had a homomorphism between them, they were called homomorphic. In some senses, they were similar to each other. A very special case of homomorphism was the isomorphism. An isomorphism is a bijective homomorphism, a homomorphism which is both onto and one-to-one as well. And isomorphisms are really very important in group theory, because if two groups have an isomorphism between them, that is to say, if they're isomorphic, then as far as group theoretic structure is concerned, they are essentially the same group. We ended the last lecture with the question, given a homomorphism, how do we tell whether it's actually an isomorphism? Or, given a homomorphism which is not an isomorphism, can we somehow cook an isomorphism out of it? We will answer these two questions in this lecture. These are the questions that we will try to answer in this lecture. And the basic tools that we will use for this purpose are two theorems called the isomorphism theorems. So these theorems are actually the main topic of this particular lecture. But before we get into the isomorphism theorems, we need to build up the background a bit. In particular, we need to introduce you to a very important subset that comes out of the notion of homomorphisms. This is called the kernel of a homomorphism. So, given a homomorphism f from G1 to G2, the kernel of f, denoted kerf, is defined as follows. Kerf is the set of all elements small g of G1 such that f of g equals the identity of the second group G2. In other words, kerf consists of exactly those elements in G1 which map under the homomorphism into the identity of the second group. Now this is obviously a subset of G1, and it's again rather obvious that this is a non-empty subset. The reason for that is as follows. We had already proven in the last lecture that for any homomorphism f of the identity E1 in G1, that is f when acting upon the identity of the first group, must give you the identity of the second group, which means that if nothing else, at least E1, the identity of the first group, will belong to the kernel of a homomorphism. So, for any homomorphism f whatsoever, the kernel is never an empty set. Actually, we will show that the kernel of a homomorphism is a lot more than a non-empty subset of a group G1. We will first begin by showing that it is actually a subgroup of G1. Now, let me remind you that we had proven some time ago that if you want to show that a subset H of a group G is actually a subgroup, all you have to really show is that for any two arbitrary elements H1 and H2 in capital H, the product H1 H2 inverse also belongs to capital H. So, using that theorem, what we will do is we will start with two arbitrary elements K1 and K2 from the kernel of the homomorphism F, and then try to see whether K1 K2 inverse is also in the kernel of the homomorphism. The obvious way to do that is to find out what happens to K1 K2 inverse under the map F. Remember, the map F is a homomorphism, that is, it obeys or respects group multiplication law. That means f of K1 K2 inverse is actually f of K1 times f of K2 inverse. F of K1 is the identity E2. F of K2 inverse is actually the inverse of f of K2, which is obviously E2 inverse, and hence the result is the identity E2. So K1 and K2 both map onto E2 because they belong to the kernel of the homomorphism, but what we have just shown is that this actually implies that K1, K2 inverse will also have to map onto E2. That means K1, K2 inverse belongs to the kernel of F for any two elements K1, K2 belonging to the kernel of F. This exactly was the criterion that we had proven is enough to show that the subset we are considering is actually a subgroup. So we have managed to establish that the kernel of F is a subgroup of G1, the domain of the homomorphism F. Before we go any further, let us take a look at a few examples of kernels of specific homomorphisms. The homomorphisms we will talk about here are essentially the same ones that we used as examples in the last lecture, but perhaps not in the same order. The first example that we are considering is that of a homomorphism between GL and R, the set of all n by n real valued invertible matrices, and the set of non-zero real numbers under multiplication. And the map is simply called det, and what it does is that it maps every matrix in GL and R to its determinant. And we had already shown before that this is a homomorphism. Let me just remind you that the fact that this is a homomorphism simply follows from the standard matrix algebra relationship. Determinant of M1, M2 is determinant of M1 times the determinant of M2, where the times here of course means ordinary multiplication. Now what is the kernel of this particular homomorphism? The answer is simple. You just look for those elements of GL and R which map under the determinant map to the identity element of the second group. For the second group, the set of all non-zero real numbers under multiplication, the identity element is of course the number 1. So all we are looking for are those specific matrices which map under the map det to the number 1. In other words, all matrices which have determinant 1. Now we already know that this is a subgroup of the group GL and R. In fact, the specific subgroup is SL and R, the set of all special linear n by n real valued matrices, that is, those n by n real valued matrices whose determinant is 1. So the fact that the kernel of the determinant map is SL and R is sort of obvious from the definition of SL and R itself. The next example that we are going to talk about is one in which the homomorphism is between the set of all integers under addition to the set Z3, the set of integers 0, 1 and 2, which is made into a group by the group operation addition modulo 3. And we had already explored what this homomorphism is in the last lecture. The homomorphism maps an integer x to the element of Z3 by this rule x mod 3. That is, you take the remainder after you divide x by 3. Now that this is a homomorphism is something that was proved in the last lecture. And here we are going to ask the simple question, what exactly is the kernel of this homomorphism? And once again, for this to be worked out, we need to be sure about the identity element of G2, which is what every kernel element has to map into. It is obvious that the identity element of the group Z3 is simply 0. So all we are asking is, what are those integers which map to 0 under the operation modulo 3? In other words, which integers leave a remainder of 0 when you divide them by 3, which is simply all integers which are multiples of 3. So kernel of this particular homomorphism is simply something you can write as 3z, which is just a shorthand for saying take all integers which are multiple of 3 and put them together in a set. And under the same operation as in Z plus, that is simple addition of numbers, it's very easy to check that 3Z is also a group, and that is 3Z is a subgroup of Z comma plus. The next example that we are going to talk about is related to an example that we discussed in the last lecture, but not exactly the same one. The map that we are going to talk about is called log, and it maps elements of R plus positive real numbers to real numbers, and the groups involved here are R plus under multiplication, that's your group G1, which maps onto R under addition. And the map is obvious from the name. It's a map which takes every positive number in R plus and maps it onto log of that number. And that this is a homomorphism is simply a way of restating the standard property of logarithms, that log of x1 times x2 is log x1 plus log x2. And what is the kernel here? Well, the kernel has to be simply the set of elements in R plus which map on to the identity element of R comma plus. Now the group of all real numbers under addition has an identity element of 0. So the question simply is, which elements of the set R plus positive real numbers map under log to 0? And you all know what the answer is. There is only one element which does that. So here, kernel of the log map has to be just a singleton set with the single element 1. Remember, as we had already stated before, the kernel of a homomorphism has to be non-empty, because if nothing else, the identity element of the first group has to map onto the identity of the second group, which means that the identity of the first group has to be in the kernel. And in this specific example, we see that only the identity of the first group, namely the number 1, is in the kernel, nothing else. The final example that we are going to talk about is directly related to this particular example that we have just covered. It's actually the inverse map for this particular one. Is a map exp or exponentiation, which goes the other way around. It takes a real number onto a positive real number, and the groups that are being mapped here are R comma plus real numbers under addition to R plus comma star, that is positive real numbers under multiplication. And obviously what this does is takes a real number x and maps it into its exponential. That this is a homomorphism is again the standard property of exponentiation that we had learned in high school. E to the power x1 plus x2 is e to the power x1 times e to the power x2. The plus and the times being the respective product laws in the two groups that we are talking about. And once again, in this case, finding out the kernel of the exponential map is trivial. All you have to do is find out which element or elements map under the exponential to the identity of R plus comma star. The identity element in R plus comma star is obviously the standard identity under multiplication, which is 1. So all you are doing is you are asking yourself which element exponentiates to 1. And there is only one such element, which is 0. So the kernel of the exponential map happens to be again a singleton set with a single element, again the identity element of the first group. In this case, of course, the first group is different and its identity element is just the number 0. So what you have is that in the last two examples, you have a singleton element as the kernel, a set with one element only, and in these two examples, obviously the single element that is there in the subgroup is the identity of the domain group. In fact, that's the only possible single element subgroup, and that is what you are getting in the two cases. In each of the four examples that we have studied so far, the kernel of a given homomorphism happens to be a subgroup of the domain. That, of course, is not a surprise, because that is exactly what we had proven a while ago. The kernel has to be. However, if you look at these examples carefully, you will realize that this is actually more than just an ordinary subgroup in each case. The last two examples, well, they are a bit special. The kernel for both of those cases happen to be singleton sets with only the identity element, and those are of course subgroups of the domain group G1, but they are also normal subgroups. As we had discussed earlier, the group with the identity alone is a trivial normal subgroup for every group. The kernel of the homomorphism for the last two cases happens to be exactly that particular trivial normal subgroup. On the other hand, if you look at the very first example, the kernel of the det map happens to be SLNR, which, if you recall, is a normal subgroup of GLNR. The fact that 3Z is a normal subgroup of Z plus is sort of trivial because Z plus is an abelian group, and for an abelian group, every subgroup has to be a normal subgroup. So, in the four examples that we have seen so far, for each case, the kernel of a given homomorphism happens to be a normal subgroup of the domain of the homomorphism. As you must have guessed, this is not accidental. This happens to be a basic property of homomorphisms F from a group G1 to a group G2. That is, the kernel F is always a normal subgroup of the domain G1 of the map F. We are going to prove this now. How do we prove this? Well, let us first recall a result that we had established some time ago, which is, if you want to show that a subgroup N of G is a normal subgroup of G, it is sufficient to prove that for all small g belonging to capital G, the conjugate group G capital N G inverse is a subset of capital N. Of course, the definition of a normal subgroup insists that G and G inverse has to be the same as N for all G, but as we had established earlier, just showing one-sided inclusion, G and G inverse is contained in N for all G is sufficient. And if you don't remember how that went, let me just quickly remind you that if small g is in a group, then its inverse, small g inverse, is also in the group, which actually means that when you are claiming that for all small g belonging to capital G, G and G inverse is contained in N, you are also claiming that G inverse NG is contained in N, which you can easily show translates to the other inclusion, which is required to prove that G and G inverse is the same as N. So let us now quickly use this particular result for the kernel F of a homomorphism from G1 to G2. So for this, what we need to show is that if we take any element small g from capital G1 and form this set G ker F G inverse, this set is a subset of ker F. That is, we will start by taking any element x from G ker F G inverse and then try to show that this x is also in ker F. And showing that is pretty straightforward. How do you show that any element is in the kernel of a homomorphism? Well, simply map that element, and if it maps onto the identity of G2, then you are done. So, what you need to do is start with this statement that if x belongs to G ker F G inverse, there has to be an element k in ker F such that x is of the form G K G inverse. That exactly is what the set G ker F G inverse is. So x is of the form G K G inverse, where k is in the kernel of F. Now what does x map onto? In other words, what is f of x? F of x is obviously f of G K G inverse, and because f is a homomorphism, is the same as f of g, f of k, f of g inverse, just using the basic property that homomorphism respects group multiplication. But now f of k is the identity in the second group, E2, So what this translates to is f of g e2 f of g inverse. Now, because your identity is sitting in the middle of these two terms, f of g and f of g inverse, you can simply replace this by f of g times f of g inverse, which by using the homomorphism property translates to f of g inverse, and f of g inverse is obviously f of the identity, in this case the identity of the first group. But as we have already seen before, under a homomorphism the identity of the domain must map onto the identity of the image. So what you have is E2. So X, this element which belongs to G ker F G inverse, maps onto the identity of the second group, so must belong to the kernel of the homomorphism F. In other words, every element of G ker F G inverse is actually in ker F. So G ker F G inverse is a subset of ker F. And that, you recall, is enough to prove that G ker F G inverse is the same as ker F, and hence ker F is a normal subgroup of G1. Now that we have studied the properties of the kernel in some detail, we are in a position to state the isomorphism theorems. So let me first state the theorems and then we are going to look at their proofs. There are two theorems, as I mentioned. The first one, that is the first isomorphism theorem, simply claims that a homomorphism F from G1 to G2 is an isomorphism if and only if the kernel of F consists of the identity of G1 and the identity of G1 only. We have already seen two examples where this was valid for the log map and the X map. In both cases, you just had the identity of the domain as the single element in the kernel, and of course these two maps were isomorphisms because they were invertible. In fact, they were inverses of each other. So at least in that example we have seen this theorem in action. We are going to prove this soon. But before I do that, let me state the second isomorphism theorem. The second isomorphism theorem tells you that if you are given any homomorphism F from G1 to G2, then in general G1 is not isomorphic to G2 because kernel of F in general does not consist only of the identity. But if you take the quotient group of G1 quotiented by ker F, and remember, because ker F is a normal subgroup of G1, you can always do that. This quotient group G1 by ker F is actually isomorphic to G2. Now, we have actually seen an example of this in this lecture. If you recall results that we had already established earlier, you will remember that SLNR is a normal subgroup of GLNR, and the quotient group GLNR by SLNR happens to be isomorphic to the group of all non-zero real numbers under multiplication, which by the way was G2 in the example of the det homomorphism that we talked about a while ago. So we have actually seen both these isomorphism theorems in action in the examples that we have seen so far. Of course, just examples don't constitute a proof. We still have to prove them. But before I prove them, let me state a very simple corollary which follows immediately from these isomorphism theorems. And this will turn out to be very, very important when we later on talk about semi-direct products. And semi-direct products actually happen to be very useful in physics, as you will soon see in a later lecture. So this particular corollary that we are going to talk about, which ultimately happens to be a very simple corollary of the isomorphism theorems, is actually a very important result. And this corollary simply goes this way. The center of a group G, ZG, which if you recall is the set of all elements of the group which commutes with every element of G, happens to be a normal subgroup of capital G. That's sort of trivial to prove. And G by ZG, this quotient group, is actually isomorphic to a very, very important group, the group of all inner automorphisms of the group G, the thing that we denote by curly I of G. We need to prove this, of course. We will do that. But let us start by proving these results one by one. Let us first prove the first isomorphism theorem. Now in the proof, what I have done is I have labeled the homomorphism by the letter phi instead of f, as I did in the statement of the theorem. Well, that's really something I shouldn't have done perhaps, but at the same time, this theorem is valid for all homomorphisms, so it doesn't matter whether it's called phi or f. At this point, let me remind you that when we defined a map to be a homomorphism, we insisted on two things. One, that it preserve the multiplication structure of the groups. That is, of course, the most important point, but we also insisted that it is an onto map. In addition to being a homomorphism, we are also demanding that kernel of the map phi is just the singleton set with the identity alone. And what we need to prove now is that under these conditions, this map phi, which is a homomorphism, is also an isomorphism. That is, it's an invertible homomorphism. By the way, the converse of this statement is almost trivial. If the map phi were an isomorphism, then by virtue of it being a homomorphism, the identity will definitely be in the kernel, and because it's a one-to-one map, then it's obvious that only the identity can be in the kernel. What we now need to prove is, of course, the direct statement that if you have a homomorphism with a kernel which has only the identity as a singleton set, then this map is an isomorphism. So what we need to prove really is that it's a bijection. We already have assumed it's onto, so all we have to do is prove that it is one-to-one. Now the way in which you show any map is one-to-one is to assume that two different elements G1 and G2 of capital G1 map to the same element of capital G2, and then show that this must lead to G1 being the same as G2. So let's try that. So we are starting with the assumption that phi of G1 is equal to phi of G2, and then let's consider this quantity phi of G1 G2 inverse. Because phi is a homomorphism, this is going to be phi of G1 times phi of G2 inverse. The times here, of course, is the multiplication law in the group G2. And then we also know that phi of G1 times phi of G2 inverse has to be phi of G1 times the inverse of phi of G2. That again is another standard property of homomorphisms. But since phi of G1 and phi of G2 are the same, then here what you are doing is you are multiplying an element of capital G2 by its inverse. So what you are going to get is the identity in the group G2. That immediately tells you that G1 G2 inverse must be in the kernel of the homomorphism phi. But since we have assumed that the only element in the kernel of the homomorphism phi is the identity E1, G1 G2 inverse has to be E1, and this immediately leads to the statement that G1 has to be the same as G2. So if two elements G1 and G2 map to the same resulting element in capital G2, then these two elements of capital G1 must be one and the same. This is exactly what we mean when we say that the map is one-to-one. Of course, we already have assumed that it's onto, and therefore it is a bijection. So what we have proven is that this map phi, which is a homomorphism, is also bijective, hence invertible, and hence it's an isomorphism. Of course, if we had defined homomorphism by just insisting that it be a map which respects group multiplication structure and not demanded that a map also be onto, then we would have to actually restate the theorem in a slightly different way. We could either start by demanding that phi, which is a map from G1 to G2, is a homomorphism. On top of that, it is onto, and kernel of phi is the singleton set E1. Then phi is an isomorphism between G1 to G2. That's one possible restatement. The other possible restatement would be, if phi G1 to G2 is a homomorphism and the kernel of phi is a singleton set with only the identity element, then phi induces an isomorphism from G1 to the subset of G2 which is the image of G1 under phi. Just think about it a bit. These two are really different ways of saying the same thing. And all this complication can be avoided if you just start out by assuming within the definition of homomorphism itself that the map is onto. And that is what we have done. Let us now turn to the second isomorphism theorem, which, remember, is a way of cooking an isomorphism out of a homomorphism. If you have a homomorphism between two groups G1 and G2, then it turns out that the quotient group that you get by quotienting out the kernel of the homomorphism from the domain happens to be isomorphic to the range. This is the theorem, and that's what we are going to prove now. Once again, in the proof, I am calling the homomorphism by the letter phi. And what we will do is we will show you how to construct an isomorphism between G1 by ker phi, that is G1 quotiented by the kernel of phi, and the group G2. So I am going to first state what this isomorphism is and then show you that this really is an isomorphism. So we define the isomorphism psi, which is a map between G1 by ker phi and G2 by this rule. Psi will of course act on an element of the group G1 by ker phi, and let me remind you, the elements of the quotient group happens to be cosets with respect to the normal subgroup involved. So in this case, the elements on which psi acts are cosets with respect to kernel of the homomorphism phi. So any given coset can be labeled by an element in the coset, let's say the element G. So small g ker phi is my coset. And what does psi do to it? By definition, that's at least the way we are defining psi. What psi does when it acts on the coset g ker phi is that it returns phi of g. So this is how you define a new map from G1 by ker phi to G2 using our original map phi, which was a map between G1 and G2. So what we will now show is that this map psi is an isomorphism. But before we even go there, the question that we should ask at the very outset is that, is this psi at all a map? Is it a well-defined map? Now why is that question at all arising? After all, what is a map? A map associates an element in the domain with an element in the range. And that's exactly what we have done here, right? We have taken an arbitrary element of the domain, g ker phi, some coset, and applied the map on it, and I have told you what the result is going to be. The result is going to be phi acting on g. And since phi is already a well-defined map which we have, phi of g is of course a well-defined result. However, the very important point that one might tend to forget here is that there are more than one ways to label a particular coset. If g prime belongs to this particular coset g ker phi, then g prime ker phi is a coset which contains g prime. It also is a coset which contains g, and that means that these two cosets are not disjoint, and hence they have to be identical. So g prime ker phi and g ker phi are the same coset. This might give rise to a problem, because when I apply psi on a given coset, am I labeling the coset by using g or by using g prime? If I label it using g, my rule should tell me the answer of psi acting on the coset is phi of g. If I've labeled it using g prime, the same rule should actually tell me that the result of psi acting on the coset is phi of g prime. That of course is a tricky situation, because one of the most sacrosanct things about a map is that a map cannot be one to many. Given a particular input from the domain, it has to give me exactly one answer from the range. Here it seems like that the way we have defined or tried to define this map may lead to an ambiguity. Let us first show that despite appearances, this problem is really not there. The map is well defined after all. Notice that if G prime is really a member of G curve phi, this coset, then there has to exist some element k in the kernel of phi such that G prime is G times k. And now our rule gives for psi of G prime curve phi the element phi of G prime. But phi of G prime is phi of Gk, and because phi is a homomorphism, that's the same as phi G times phi k. But notice k is a member of the kernel of the homomorphism, which means phi k is, of course, E2. So the result is phi G times E2, which, because E2 is the identity, is simply phi G, and phi G, remember, was what our map psi gave to G curve phi. So G curve phi and G prime curve phi may be two different ways of labeling the same coset, and because our rule singled out G as the one on which phi is going to act to give you the result for psi, it appeared that there was a possible ambiguity, but as you can see, there is none. No matter which element from the coset you take to label the particular coset, you end up with the same result for psi acting on that coset. So you can choose whichever element you want as a label, apply phi on it, you should get the same result. So this map is definitely well defined. Let us now go on and show that this is an isomorphism. Of course, to prove that this is an isomorphism, we have to show two things. Firstly, that it is invertible, and secondly, that it is a homomorphism. Let's first show that it is a bijection, that is, it's invertible. Now, to be a bijection, of course, it has to be an onto map. Since the map phi is onto, it follows rather trivially that so is the map psi. I will not explain this any further, but a moment's thought will tell you why this has to be the case. Now, is this map also one-to-one? That is, if two different cosets, or rather two cosets, G1 curve phi and G2 curve phi, both give you the same result under the action of the map psi, does it follow that G1 curve phi is the same coset as G2 curve phi? If it does, then it is one-to-one, otherwise it's not. So let's see. If psi G1 curve phi is equal to psi G2 curve phi, then obviously this really implies that phi of G1, which is psi G1 curve phi, is the same as phi of G2, which is psi G2 curve phi. But now, this actually tells me that phi of G1 G2 inverse is phi of G1 times phi of G2 inverse. Remember, phi is a homomorphism. And therefore, it's actually phi of G1 times the inverse of phi of G1, and hence it's E2. So G1 G2 inverse actually gets mapped onto the identity when phi acts on it. And that immediately tells me that G1 G2 inverse must be an element of the kernel of phi. Remember the proof of the first isomorphism theorem? There also we had a very similar result, and G1 G2 inverse was shown to be in the kernel, but there of course the kernel had only a single element, the identity E1. Here we have made no such assumption. So G1 G2 inverse is some arbitrary element of the kernel of phi. But then this implies that G1 belongs to G2 curve phi. So G1 and G2 essentially belong to the same coset with respect to curve phi. And that immediately tells me that G1 curve phi and G2 curve phi has to be the same coset. Therefore, if the map psi gives you the same result on two cosets, then these two cosets have to be one and the same. Hence, psi is one-to-one, and because it's already onto, it has to be a bijection. So what is left? What is left is to prove that psi is a homomorphism between G1 by curve phi and G2. Of course, the only weapon that we have here is the fact that phi is a homomorphism. So we are going to exploit that. So what we need to show is that when psi acts on a product of two cosets, G1 curl phi times G2 curl phi, it produces psi acting on G1 curl phi times psi acting on G2 curl phi. But let us first proceed with what we know about this multiplication of two cosets. We already know that if you multiply a coset G1n with another coset G2n, where n is a normal subgroup, then the result is G1 G2 times n. So applying that, what we get is this is equal to psi acting on G1 G2 curl phi. But I know what psi acting on G1 G2 curl phi is. By our rule, it has to be phi of G1 G2. And now that we have brought phi into the picture, we can use the fact that phi is a homomorphism. So this has to be phi G1 times phi G2. But what is phi G1? It's nothing but psi of G1 curl phi. What is phi G2? It is psi of G2 curl phi. And therefore, psi of G1 curl phi times G2 curl phi is psi of G1 curl phi times psi of G2 curl phi, which exactly is what you mean when you say that psi is a homomorphism. So we are done. We defined a map between G1 by curl phi and G2. We showed that it is an unambiguous map, so it's a proper well-defined map. Then we showed that it is a one-to-one onto map, so it's invertible. And finally, we have shown that it's a homomorphism. So this map psi ultimately is a bijective homomorphism, hence an isomorphism. And because we have managed to show that an isomorphism exists between G1 quotiented with the kernel of the homomorphism and G2, these two groups have to be isomorphic to each other. Of course, it should be rather obvious that if we had not insisted that the map phi, this homomorphism, also be onto as part of the definition of a homomorphism, then the restatement here would have been G1 by curl phi is isomorphic to the image under phi of G1, which is a subset, of course, of G2. With these two theorems under our belt, let us just try to use them to prove the important corollary that I mentioned earlier, which is the statement that if you quotient out the center of a group from the group, that is, you form the quotient group G by ZG, the resulting group is actually isomorphic to the group of all inner automorphisms curly I of G. So the way in which we are going to prove this is basically we are going to construct a homomorphism between capital G and curly I of G and show that this homomorphism is a kernel which is the center of the group. And then, of course, the result would follow trivially from the second isomorphism theorem. By the way, an important corollary to this corollary happens to be the following. If the center of a group turns out to be the singleton set with only the identity in it, then obviously G quotiented by the center is actually isomorphic to G. So what we end up with is, in that case, the group of all inner automorphisms of capital G is isomorphic to capital G itself. Now let's go ahead with the proof. And as I have said, the strategy here would be construct a homomorphism between capital G to curly I of G, which of course is the group of all inner automorphisms of capital G. Now, I have to define this map phi, and the most obvious way to define the map phi is to map small g, an element of capital G, to the inner automorphism generated by small g, Ig. Let me just remind you what Ig does. Ig is an automorphism, that is, it maps capital G to itself isomorphically by the following rule. Ig, when it acts on any group element G prime, produces G prime G inverse. So basically it induces conjugacy by G. With this reminder in place, let us consider Ig1 G2 acting on an arbitrary element small g of capital G. So what is Ig1 G2 acting on G? By definition, it is G1 G2 G, then followed by the inverse of G1 G2. But G1 G2's inverse, remember, is G2 inverse G1 inverse. So if you use that and use associativity to change my brackets around, I get G1, then G2G, G2 inverse, and finally there's a G1 inverse on the right. So this expression here, of course, is Ig1 acting on this argument. So it's Ig1 acting on G2, G, G2 inverse. But G2, G, G2 inverse is Ig2 acting on G. So this is Ig1, Ig2 acting on G. So since this works for all G, this immediately follows that Ig1, G2 is Ig1 followed by Ig2. Remember, two maps following each other is exactly the multiplication rule when the elements involved are maps. They actually multiply, quote unquote multiply, by composition. So what we have managed to prove here, phi acting on G1, G2 is phi G1 times phi G2. Hence this map phi is a genuine homomorphism. What we need to prove, of course, is that it's also onto, according to our definition of a homomorphism, but that is rather trivial because after all the inner automorphisms are exactly of the form Ig for some G. So ontoness is sort of trivially established here. What we need to do now is to prove that the kernel of this map phi happens to be the center of the group G, which is all you really need to show that G by ZG is isomorphic to this group of inner automorphisms, curly I of G. So let's try showing that. So let's try first by taking an arbitrary element from the kernel of this phi. What that means is this, under the map phi, K gets mapped, of course, to Ik, but Ik has to be the identity of the group of inner automorphisms, which is nothing but the identity map. So Ik is ID, the identity map. So what this tells you is that for all G belonging to capital G, Ik acting on G has to give you back G, because that's what the identity map does. However, Ik acting on G by definition is Kg K inverse. So this tells me that Kg K inverse has to be G, and hence Kg has to be equal to Gk. Remember, this is true for all small g belonging to capital G. So what this has established is that this element K in the kernel of phi has to commute with every element of the group, and hence it has to belong to the center of the group G. So what this does is tells us that every element of the kernel of this map phi has to be in the center of the group. So kernel of the map phi has to be a subset of ZG. Our aim, remember, is to prove that these two sets, kernel of phi and Z of G, are exactly the same. What we have done is we have shown one-way inclusion, that is, kernel of phi is a subset of ZG. What we need to show is that the inclusion also works the other way. And for that, let us pick an element, small z, from the center of the group ZG. Then, of course, by definition, for all small g belonging to capital G, ZG must be equal to GZ. That's exactly what the center is. And that immediately tells you that ZG Z inverse is G. So IZG is G for all G, and that exactly tells you that IZ is the identity. And since IZ is what Z maps to under phi, if that is the identity, it tells you that Z must be in the kernel of phi. And hence, every element of the center is also in the kernel of phi. ZG must be a subset of kernel of phi. Hence, both sided inclusion has been proven. Kernel of phi is the same as ZG. And that's all you need for the proof. Remember, we have already shown that there is a homomorphism phi between G and curly I of G. And this homomorphism happens to have a kernel which is the center of the group. So the second isomorphism theorem would immediately tell you that G by ZG is isomorphic to IG. Let me end this lecture by trying to give you some insight as to what these isomorphism theorems really mean. Now, there are actually many different ways in which you can think about this, but I myself find this particular approach or particular way of thinking about these things rather useful. What the first isomorphism theorem says is that if you have a map which preserves group structure, then all that you need to ensure that it is not many to one is that the inverse image of one single element, the identity of the second group, happens to be a singleton set. If you think about it a bit, you could have used some other element rather than the identity. It's just that the identity is the easiest to think about in this context. At this point, I should also point out that if you were talking about an arbitrary map between two sets, the inverse image of one point in the range being a singleton set has no bearing whatsoever on the inverse image of the other points also being singleton sets. If a map is 1 to 1, of course you expect the inverse image of every point to be a singleton set. Now this is what is ensured in the first isomorphism theorem via the fact that the map that we are talking about is not an arbitrary map between two sets, but it is a structure preserving map, a homomorphism. So that has to be borne in mind. It is actually more interesting to think about what the second isomorphism theorem means. Notice that when you say that the map F between G1 to G2 is a homomorphism and not necessarily an isomorphism, what you are really saying is that it's possible that there could be multiple elements of G1 which map onto the same element G2. What the quotienting operation via ker F does is that it actually collects together all those elements in G1 which were mapping onto the same element in G2 and identifying them all together as a single element. So basically, this identification of multiple elements and wrapping them all into one is exactly what the quotienting operation is doing here, and that is why it ends up giving you an isomorphism. We will see plenty of physical examples where this kind of identification of different elements into one plays a very, very important role. At this point, I don't really want to spend too much time on giving you physical examples of this thing happening, but let me just point out that you have infinitely many different magnetic vector potential configurations, each of which give you the same magnetic field. So if you're really interested in the physics, what you will do is wrap all these different magnetic vector potential configurations together and treat them as the same magnetic vector field configuration. This kind of quotienting is actually very, very useful, as this example should sort of indicate to you. In the next lecture, what we are going to do is we are going to talk about the ways in which you can build bigger groups out of smaller ones via two very important processes, direct product and the semi-direct product. It so happens that both of these have immense applications in physics. So until then, goodbye.